Hello everyone. In this video, we will do some examples for checking the invertibility of a linear vector field. A matrix is given and the question is the vector field defined by this matrix invertible or not? Well, remember that if you have a matrix, then you can define an n by n matrix, in this case 3 by 3 matrix. You can define a vector field by this matrix multiplication. The question is this an invertible vector field or not? Well, remember the magical number. Always, to check the invertibility, you can start with the determinant of the coefficient matrix. Is determinant 0 or not? Well, let's see. Here, okay, so I'll go along the components of the first row, then the first column, that's 5 times determinant of the remaining, which is 3, 0, negative 2, 3. Then we get rid of this one, and then do the second column. The component is there, but for the second column, you always remember you put negative 2, so negative 2 determinant of the remaining, which is 6, 0, negative 1, 3. And then get rid of that part. And now it's turn for the third column, which is given by, okay, so the intersection is 1. So plus 1 and determinant of 6, 3, negative 1, negative 2. Here then I get 5. 3 times 3, remember for the 2 by 2 matrix, this is 9. Minus 0 times negative 2 is 0. 6 times 3 is 18. Minus, 0 times negative 1 is again 0. That part is 6 times negative 2 is negative 12. Minus negative 1 times 3 is negative 3. So this will give me 45. This will give me 36. This guy here is 9, minus 9, and that is what we have. But you see that if you add these guys, this is 0. So what we checked, what we figured out is that the determinant of the coefficient matrix is 0. So that implies that if the corresponding linear vector field is not invertible. Okay. Well, then if it is not invertible, find me that non-zero vector which is mapped to the origin by this vector field, because that was another equivalent condition that we had. So basically what we're interested in seeing what vectors, or which vectors x, y, and z are mapped to the origin. In other words, find all these x, y, z's such that this guy is 0, 0, 0. Okay, so this means that I have to solve an equation. The equation that we get them from this multiplication of this matrix to that column. But there will be 3 components, so there will be 3 equations. 521.xyz, this will be 5x plus 2y plus z equals to 0. 6x plus 3y equals to 0. Minus x minus 2y plus 3z equals to 0. Note that this step will become very important for us later on when we're trying to find the determinant, the eigenvalues and eigenvectors. So better to make sure that you know how to deal with this linear 2 by 2, 3 by 3 system of linear equations. The method you need to know is just elimination of variables. Here I see that this second equation doesn't have any z, so let's just use the first equation and third equation and get rid of z in those equations. And well, when you get rid of one variable, the next, it will be easier to handle. Okay, so to get rid of this z in this case, what I need to do is that let's multiply the first equation by 3 and then subtract it from the third equation. That will give me, 15 minus negative, so this is 16x, 6 plus 8y, and that will be 0z. Very nice. So I use equation 1 and equation 3, and I generated a new equation which only has two variables, x and y, in it. Now I have two equations with two variables, 6x plus 3y equals to 0, 16x plus 8y is equal to 0. Now, do the same thing. Choose one of the variables, eliminate that variable, and go ahead. So in this case, I can get rid of, for example, y. So what I do is that I multiply the first equation by negative 8, the second equation by 3. If you do that, what you will notice is that that is negative 46x plus negative 48x plus 48x. So this will be 0x, and then you have 0y equal to 0. So what we found was 0 equal to 0. This means that you're on right track. It means that these two equations are basically the same thing. So considering both of them wouldn't give you anything more than just considering one of them. So I ignore one of these guys and I just go ahead and write this, the first equation, and try to solve it. Well, there are two variables. That means the only thing that I can do is I can write one variable in terms of the other one. But this has something to say. It says that the second component is negative 2 times the first one. Okay, that is a piece of information I can use. But how about the third component? Well, I can use any of the equations left there and plug in that one, y equal to negative 2x, so it will be 5x plus 2 times negative 2x plus z is equal to 0. That will give me z is actually equal to negative x. And this has another thing to tell me. This says that the third component is negative of the first one. What I found is now interesting. It says that every vector of the form, the second component is negative 2 first component, the first component is x, and the third component just negative of the first one. Any vector of this form is mapped to the origin. Well, in particular, if x is equal to 1, then we have non-zero vector -1, -2, -1. Or when x is equal, say, to any number you put there, then that will give me another vector another vector which is mapped to the origin by this f. And well, that is what we were looking for. Yes, the matrix, the matrix defines a linear vector field which is not invertible, and all the vectors of this form are mapped to the origin by this vector field.